Yes, we are in the right time. So it's a pleasure to introduce Mackezie Powers, who will speak about two default Hamiltonian paths and ideals of ground POSETS. So, please.
Well, thank you, and thank you to the organizers for inviting me. I'm really sorry I couldn't make it. I tried, like Lucia said, I tried twice on Sunday and on Tuesday to get a flight here to Brazil, and they were both canceled because of weather in the eastern United States. As Daniel might say in one word, that's life. And to start this presentation, I just wanted to say a couple words about my time with Daniel. I met him in 2017. I was just finishing my master's, and I was not very happy with the subject I was in, and a friend of mine invited me to just visit a class that Daniel was teaching on finite fields and coding theory. And after one class, I think just Daniel's energy and his knowledge and his attitude, and especially his handwriting and Blackboard organization. I don't know if anyone else has mentioned that, but he's a master of organizing his notes on a blackboard. Yeah, I wish I had learned that skill from him because I'm still very rusty there.
On the handwriting, you went a little bit too far. Organization, yes, but
anyway, I found myself very interested, and I almost immediately after I asked if he'd be willing to supervise a PhD, and this is part of our work on that project. This is an ongoing project with Daniel PANARIO, with LUCIA, and with CLAUDIO QURESHI. I wish I had pictures, but sorry, I don't have any pictures. So this is a talk about combinatorics and generating combinatorial objects. The starting point is the poset. I hope everyone knows what a poset is, but very quickly, it's a ordering relation on a finite set, or at least in this context, a finite set. In particular, we don't necessarily have comparability between any two elements. So some elements might not have a relationship between them in this ordering. We will use a graph representation of a partial order, with vertices, all of the elements in that set, and an edge between two elements, x and y, if x is greater than y in that poset. And we remove all the intermediate edges. So here's an example, a very simple poset. We have 6 elements, 1 to 6, and we have 4 relations, or at least 4 non-trivial relations. And here is the picture. So if you can't tell 1 greater than 3, we have 1 above 3 in this graph. This is often referred to as a Haas diagram. Am I still connected?
Yes.
Yes.
Okay. So the object we're interested in enumerating here is the ideal of a poset. It takes the language, I think, is borrowed from ring theory, and the defining characteristic is very similar. We say a subset of a partial order is an ideal if it satisfies this nice closeness property. If I is an element of that ideal and another element is less than that element with respect to that poset, then that element J must also be a part of that ideal. We have this notation sometimes, the ideal generated by a subset of elements in that poset, which is just these large angle brackets. Here's an example. The same partial order as before with the same diagram. We're looking at the ideal generated by the single element 1 here, in other words, 1 with these angle brackets. And I've highlighted in green the ideal generated. So 1 is bigger than 3, 1 is bigger than 5 with respect to P. And so all 3 of those elements are contained in that ideal. One thing that has been done is, one thing that we can do is associate each finite poset to an ordered lattice. For this talk, we can consider that to just be a poset itself of its ideal. So we can organize the ideals as another partial order. the vertices of that poset will be the ideals themselves, including an empty set ideal. And the ordering is kind of natural. It's just the kind of subset order. So if one ideal is contained in another, then it is less than that ideal in that poset. And we can draw the hash diagram of that in the same way as before. So here's a slightly simpler example, a very small poset, 1, 3, and 5. And here's the lattice of order ideals for that poset. And the nice way to write it is sort of from smallest ideal to largest. So the smallest ideal is the empty ideal. The second row here is the ideals containing one element. Here's the ideals containing two elements, and so on. And as before, we don't include intermediate edges in that graph. So why is this interesting? I guess it's interesting for anyone who's interested in just generating combinatorial objects. The main question is, how do we list all of the ideals of a poset? And there are algorithms to do that. There are pretty fast algorithms to do that. In enumeration, we're often focusing on reducing the delay between outputting ideals. With a little bit of thought, you might be able to convince yourself that the number of ideals is exponential in the size of the poset, depending on the poset. So we can't pretend we'll come up with a fast way to list all of them, but we can at least focus on the time between each element in that list. A typical strategy is to use gray codes. So try to find a list with minimal changes between successive objects, which often can translate to less work per object, less delay, and therefore less overall time generating the entire list. When successive items differ by one element, we call those lists gray codes. If you're familiar with gray codes, often the problem of finding a gray code is equivalent to finding a Hamiltonian path in a certain graph. Usually this is in the context of n-dimensional hypercubes, but we'll use something a little bit different, a little more general. But in the case of posets, this is equivalent to finding a Hamiltonian path in the hash diagram of that lattice of ideals, J of P. So here's the previous example. We had the poset P, and we had that lattice of ideals, J of P. And we're asking, how do we list all of these ideals, 0, 3, 5, 3, 5, and 1, 3, 5, in a gray code order? Well, because there's no Hamiltonian path in this graph, our conclusion is that we can't list them in gray code order. And again, the 0 ideal we don't include in that list. However, if we relax the condition on gray codes just a little bit, and we allow not only difference 1, but differences of 2 between successive items, which is equivalent to saying we allow additions, deletions, or swaps of elements, then that new graph does have a Hamiltonian path. So these are almost gray codes, or these are 2 gray codes. But this is a known result in this field that if we do relax that restriction, we can make this list. And therefore, we can do it pretty fast in those cases where we do have Hamiltonian paths. Here's that previous example where I've just added this swap between these two elements here. And now instead of having to add or remove elements, we can just swap 3 and 5, and that becomes a Hamiltonian path through that graph. So this problem has been worked on. There have been many updates since the 90s. A recent one in 2012 gave an algorithm listing all of the ideals in log of n amortized time per ideal, with this swap condition being allowed, with the slightly relaxed definition. A conjecture and an open problem in this field is whether or not there exists an algorithm that lists these in O of 1 amortized time per ideal, which would be optimal in this situation. So we'll leave that problem open because as that problem was being proposed and worked on, kind of a side problem was also proposed, which was what if we're not trying to list all of the ideals of a poset, but instead just the fixed size ideals. So for example, the ideals of size 3 of a poset. And can we list them in gray code order? what brought this problem to our attention partially was an algorithm in 2021 that solves this problem with time proportional to the largest anti-chain in the poset. So an anti-chain is sort of is a sub-poset with elements that are not related at all. Remember, in partial orders, we don't have to have relations between every element. And as with the more general case of listing all of the ideals, we can convert this problem to a graph problem. So we define this graph JPK consisting as vertices of all the size k ideals of that poset, and we draw an edge between any two k ideals that differ by a swap. This is equivalent to saying the strings have Hamming distance 2. So here's a nice example. Here's a poset. I've called it FE6. I'll talk about that a little bit later. Without describing the poset explicitly, hopefully you can kind of tell what the relations are here. So 6 is greater than 5 and is not related to everything else. 4 is greater than 3 and 5. Hopefully we can read off those relations just from this hash diagram here. And here's the associated graph. And you can see I've drawn in bold here a nice Hamiltonian path through those ideals. And this was conjectured by Pruesse and Ruskey in 1993 that this graph actually does have a Hamiltonian path. So kind of in contrast to the more general case where we can come up with counterexamples, or they found counterexamples and they proved that you had to relax the condition to find a Hamiltonian path every time. They conjectured that this fixed sized problem is solvable in every case. Now we don't think they had access to maybe the same computing that we do, because I'll say in a few slides that it didn't take us very long to find counterexamples to that. However, I think the reason that they believed it so strongly was that they verified it for very large classes of partial orders. There's the series parallel posets, which they verified in that kind of same paper that proposed the problem. This includes trees. This includes NRT posets. This includes a lot of posets that have a kind of recursive structure. A few years later, other authors proved a similar result for the interval orders, another famous class of partial orders. So we were reading about this. We were doing the background over the summer, and we tried to come up with a project. And part of that process was typing into Google, what are some posets that aren't parallel, series parallel, or interval orders? And we found the fence and the crown posets. So this was our original proposed project, was just to verify the conjecture for these two families of posets and refine that conjecture. So here's the fence poset. I showed you this poset before. I showed you the diagram associated to it. And it has a very simple order structure. Just all of the even elements are bigger than the next two, or the previous and the next odd element. So here's the fence containing 6 elements.
Yeah.
The nice thing about fences is that they have a very straightforward recurrence identity, at least when you're talking about the ideals. And it looks messy here, but the picture is a little bit easier to understand. It's not too hard to construct the ideals of a fence based off of 2 smaller fences. So imagine we have an ideal of this fence with 6 elements. We partition those ideals into, depending on whether or not they contain the element 6. If they do contain the element 6, remember ideals, if you contain an element, an ideal contains every element less than that. So if you contain the element 6, you also must contain the element 5. And then you're just selecting one or k minus 2 elements from this smaller fence, the fence with 4 elements. And likewise, if you decide my ideal will not contain the element 6, well, you're just looking at k ideals of the fence 1, 2, 3, 4, 5. So this recursive nature of fences led us to a nice result about the Hamiltonicity of the ideals of fence posets. Our theorem is that the fence poset has a complete set of Hamiltonian paths for all n. So complete set of Hamiltonian paths is slightly stronger. It's a set of Hamiltonian paths with some relationships between them. But we're able to take advantage of that, this recursive definition of fences to put together nice sets of Hamiltonian paths for the fence posets. So I think we're happy with this result, that this verifies part of our project. So what about the crown posets? And I know I wasn't aware of crown posets at first, but Claudio pointed them out to me and said, hey, they might actually be easier than fences because they have this nice symmetric structure. A crown poset looks just like a fence poset, except you have one extra relation, and that's the kind of last even element is also greater than the first odd element. So here's the crown poset with 6 elements. And you can see they have a lot of symmetry. You can flip them, you can shift them. They have this very nice cycle structure. However, maybe we should have known crown posets often appear in the literature as counterexamples to certain problems, and this is not an exception. So almost the first crown that we checked failed to have a Hamiltonian path in its graph of ideals. So here it is. It's a proof kind of by picture. Here are all of the 3 ideals of this crown here, and here's their connection, and we can see there's no way to draw a Hamiltonian path between any pair of elements. In fact, we came up with a lot more counterexamples that have this structure. That's not really part of this talk, but we did find many more. So this is not the only counterexample. But we did ask, at least for crowns, whether or not this is the only counterexample for k equals 3. So in this case, we're looking at the 3 ideals of the crown with 6 elements. And we came up with a strategy involving just kind of a simple strategy just involving subsets of natural numbers. And here's the explanation. It's a pretty clean construction. So here's the crown poset with 8 elements. We kind of partitioned the ideals into whether or not they're entirely on the bottom. So as in, they don't have any relation. They're not bigger than anything else. They're not related to each other either. So in this case, 1, 3, 5, and 7 are the bottom. And here are the ideals entirely on the bottom. And you can see there's 4 elements. And if we've said k equals 3 here, we're looking at the 3 subsets of that set of 4 elements. The other ideals are those containing an even element, an element on the top. Now, if you notice, let's say an ideal contains the element 2, it also contains the element 1 and the element 3. So we already have all 3 of the elements we're prescribing here. So the 3 ideals with elements on the top look like these kind of short sequences of integers, 1, 2, 3, 3, 4, 5, and then 7, 8, 1, because it has to wrap around. It has this cyclic structure. So our strategy was, let's work on the bottom part, the part that we have a little more control over, the part that doesn't have relations between each other. So these are just 3 subsets of n. Our strategy was, can we list these in a way that lets us insert the top parts in an obvious way? So in particular, can we find a cycle of the 3 ideals on the bottom containing all of those intersections that are adjacent? So in this case, we ask for 1, 3, 3, 5, 5, 7, and then 7, 1, so that we can insert the corresponding even elements here. We called this pair-adjacent or PA cycle. And here's an example for that case. You can see I've labeled the edges by the intersection between the successive subsets. Once you have this labeling, it's very easy to insert the remaining ideals here. So for example, between 1 through 5 and 1 through 7, because their intersection was 1, 3, we inserted the ideal 1, 2, 3. a side note about the Johnson graph. The Johnson graph is simply a graph with vertices, all of the k subsets of the integers less than or equal to n, with edges drawn between two vertices if they differ by a swap. So it's exactly what we were doing on the bottom part of the crown here. Famously, the Johnson graph is known to be Hamilton connected, which means we can find a Hamiltonian path between any 2 points, any 2 vertices. So it's a pretty strong result. And this is why, and we wanted to exploit that. We wanted to say we know something about the Johnson graph, and can we find cycles of the Johnson graph with this nice intersection property between successive ideals. Here's the example I chose here, a very simple one, the Johnson graph 4, 2. So we're looking at the 2 subsets of the set 1, 2, 3, and 4, and here's their connections. So with that previous construction in mind, just coming up with these PA cycles in the Johnson graph and then inserting the top part, the peaks, the even elements as appropriate, we came up with a pretty simple characterization of Hamiltonian cycles in the 3 ideals of the crown. And that is, the Hamiltonian cycle exists there if and only if a PA Hamiltonian cycle exists in the Johnson graph, isomorphic to the bottom part of that poset. Our first effort here was to give a direct construction of these objects, these PA cycles. And we did that, and I think Daniel might be disappointed because I know he really liked this construction. It was a visual construction. It had a very simple kind of inductive argument. But I decided for this presentation to skip to our more recent result, which is a generalization of this. So we did prove that the Johnson graph has PA cycles, and so therefore the size 3 ideals of crowns have Hamiltonian cycles. Claudio suggested a generalization, and he called it T-full Hamiltonian cycle. So before, in the previous example, we only needed the intersections to contain those adjacent pairs, 1, 3, 3, 5, 5, 7, and so on. But Claudio asked, why can we find a Hamiltonian cycle that has any kind of family of subsets? And in particular, what if we say we want to find a Hamiltonian cycle so that every subset is found in the intersection of successive combinations, successive subsets. So here's our definition. We have a map between the T subsets of size n, of the set 1 to n, to the edges of some cycle, such that that edge contains, the edge corresponding to some T subset T is contained in the intersection of some adjacent vertices on that cycle. So you can see it's much stronger. Before we were only looking at a few adjacent pairs, and now, for example, if T equals 2, we'd be looking at every single pair, asking whether or not those exist. So our main contribution to this project so far has been, I think, this theorem, which says that we can actually find these things. I think that's the easiest way to say it, is that the Johnson graph of size k, when it makes sense to ask this question, when the number of subsets of size t is less than the number of subsets of size k, does contain a T-full Hamiltonian cycle. It's a little bit stronger here. We have it between any 2 vertices that are distance 2. But that's just saying we just use some permutations there to get that extension. The proof of this was partially due to a hint from a reviewer to our first submission for the previous work for k equals 3, and the proof involves a very recently proven result about the hypercube called the middle levels theorem. I mean, it was actually, I have this reference here, which is the easiest to read proof that was published by Mackezie, but I think it was proved as early as 2014 or maybe 2016. The middle levels theorem, we won't talk about it too much, but but it's been long-standing for at least 30 years. So I think we're happy to be able to use it to prove something that we found challenging. We split the proof into two parts, kind of straightforwardly, into what depending on the relationship between k and n over 2. So kind of an upper and lower half. The first part is this kind of direct consequence of the middle levels theorem, and the second part is a constructive argument by induction, again relying on the middle levels theorem on the hypercube. Why is this interesting for the case of crown posets? We were able to use this idea, the idea of T-fullness, and in particular the idea of two-fullness. So just looking at the two subsets, making sure we have all possible pairs, to find Hamilton cycles for crowns of all sizes. So here's our theorem. If we have the integer k between 0 and n-2, inclusive of n-2, then that graph, that lattice of ideals of size k of the crown contains a Hamiltonian cycle. I think I'm good to finish this last slide. So, you know, this like the crown has 2n elements, and we've stopped at n-2 here. So it seems like we're still, you know, less than halfway done, in the sense of we'd like this graph to be Hamiltonian for all values of k, you know, minus the counterexample we found. Some positive news here is that we can exploit the structure of crown posets to expand this result slightly. A known fact about crowns is that when you flip them, when you take the dual poset, so that dual poset is isomorphic to the original crown. So here I've given the previous crown poset with 8 elements, and then I've flipped it, so to speak. So all the relations, if 2 is greater than 1, now 1 is greater than 2 in the dual. This gives us a nice correspondence between k ideals and 2n minus k ideals. That is, if we have a Hamiltonian cycle in the k ideals of the crown, then we also can find a Hamiltonian cycle in the 2n minus k ideals of that same crown. And so this really kind of completes, you know, minus these 3 cases. If k is equal to n-1, k is equal to n+1, or k is equal to n, we don't have a conclusive argument yet. But other than those 3 cases, n-1, n, and n+1, we have a proof that that graph of k ideals of the crown poset contains a Hamiltonian cycle. Some future ideas here for this project. You know, this week in Brazil, we were intending on trying to finish this theorem, finish those last 3 cases, but that didn't work out for obvious reasons. Later, we have some results on height 2 posets in general, and we'd like to continue that work, see if we can complete that case, find the conjecture for all height 2 posets. We have some results, mostly from contributed by Claudio, about looking for T-full Hamilton cycles or paths in the Johnson graph between any 2 vertices. So our theorem finds T-full Hamiltonian cycles between, you know, any two subsets that are close enough together, that are distance 2 apart. But we ask, just like the Johnson graph, can we find T-full Hamiltonian paths between any 2 ideals of size k, or excuse me, of size k? And you know, long term, the big goal would be to refine the conjecture of Pruesse and Ruskey as much as possible. And so that's everything I have for you today. Thank you very much.
Okay, so any questions or comments? Questions? Well, if not, let's thank the speaker again. Thank you.
La tecnología aquí. Sabe que the lights.
Okay, so next speaker. Next speaker will be LUCIA MOURA from University of Ottawa. She'll talk about new families of string 3 over arrays using factors.
Thank you. And this is the test that I know how to click. See, no picture.
Lucia, we were all expecting the nice pictures, huh? From you.
Oh, my. Get distracted and I won't speak. Okay. Okay, so I will be talking about new families of strength free covering arrays using LFSR, linear feedback shift registered frequencies from finite fields. This specific work that is in the abstract is trying to work with my PhD student, Ken Shocker. I chose this topic because this topic of looking at LFSR sequence came about from my first joint work with Daniel, Brad, and Stephen. When around 2005-06, he showed us, oh, I found this paper by Munemasa, and it's talking about polynomials on finite fields, and it's to find orthogonal arrays. Brett and I were working covering arrays, orthogonal arrays, and I said, maybe we can do something. And that's how my story with this topic started. And also, it's something I'm working until now, because this was a paper that I said it was submitted when I submitted the abstract, but now we just got news that it was accepted, my notification. So it's something I have been doing for since then, So here we go. So that's the script of the talk. This is just one slide, don't worry, I'm going slow. But please, can you tell me about when I'm at 15 minutes, so I know that I have only 10 more. So I will talk first about the introduction about LFSRs, or how to build a orthogonal array for LFSR. Thanks, Kirsten, and thanks both Kirsten and Andrea, because several definitions are going to repeat, so people are going to get more, they already have some intuition and understanding of those. So we're going to talk about this, then I will talk about how to use this to build some covering arrays. This is the result of 2014 with rapports. Then I'll talk about the present work. And in the middle, there may be some things that Daniel did. But not a lot, but we just submitted this area, and we did that nice paper that had the approval case analysis of 375 cases that we divided between the costs. 72 pages that were not published, but was put in the archive to say that all these cases work and the result. It wasn't approved from the book, but nonetheless it was approved. Oops. Oh. Daniel, when I met him, this makes May 88. That's when I met you in 89, I think. No, 88, maybe this is a renewal of your card, because you started in 87. The graduate program in the University of São Paulo. Full name, for the ones that don't know.
Thank you.
Daniel. He likes to hide this as, he likes to hide his age, but they are now the cat is out of the box.
So, but are you sure this is not Lula? At the time, Lula at the time.
Okay, so as I was telling you, that is this important joint work, but I'd like to also mention my main collaborator, most important collaborations with Daniel, with you guys. Some of them you saw in smaller sizes in some of the pictures, Nathan, 33, Diego 20, and Lucas on the back there, the corner, 56. But now let's go to less important joint work, but the first, which is when we were at POSET. Yes. Oh, I want to point and I'm clicking. So this will happen. So he said, take a look at this paper. This was around 2005, maybe when we started this. This was published at this age, right?
Actually, I saw the paper when it came out in FFA, and I thought, oh, this is a great idea, but I was working on something else. Maybe I come back one day, and I forgot about it. And then I saw it again in 2002.
Mm-hmm.
And then I grabbed Brett, and you say, well, and no one, no one cared about what I was saying, I guess. And eventually, like in 2004, you and Brett said, yeah, we should work on this.
Yeah, so orthogonal arrays, primitive trinomials and shift register sequences. So it was about trinomials, not dividing trinomials, and some conditions for then these giving orthogonal arrays. These orthogonal arrays are strength 2 and almost the strength 3. Okay, so this is the first joint work. Doer, I couldn't find his picture on the web, but I could find that he published a book on problems in the theory of modular forms. Now, it changed, but at this time he was an undergraduate at Carleton, and then we got this problem to work. And, you know, the generalization was to consider pentanomials not divisible by trinomials, for example. Okay, after that, Daniel, Stephen, and another student generalized, because this was for F2, generalized for F3. Then comes this other work, which was Brett Stevens, that we've seen a lot. We've seen a lot of his papers as well. And our joint student, Sebastian Brackhurst, then we have this result here, which will be important for this talk, which is constructing strength 3 cover arrays from two almost strength 3 orthogonal arrays. And this gives you problems. We try to extend the 4-4 with Xanakis, a Greek student of Daniel. We had some interesting results in this paper, but they were more computational. We were trying to find what's, how we can do similar things the best we can do. Use a backtracking to see how large it could be the number of columns of these arrays that comes from pasting two orthogonal arrays coming from LFSI. Then came my first Brazilian student that just came, gave a talk, André Castoldi, came to Otto, and in various meetings, including some in our basement, we came up with something to a related object called order orthogonal arrays, and we also use the same machinery with the LFSIs. I won't talk about all of this. I will focus on some things here. Something else, character sums for covering arrays,
existence of covering arrays using character sums.
And then this one is a generalization, I think, of what we did, André. But now the polynomials don't need to be primitive, right? Well, now this other thing here is a very interesting paper by Coburn and others about, connects a big connection with this geometry, right? That we already knew, but they did a lot of interesting things. Sets of mutually orthogonal projected and affine planes. Basically, it's a rereading of, for example, results like the one in Raphars in terms of geometry and properties of projected planes or affine planes. Then comes this work here that I will talk about with Taylor, so I won't explain here. And I will give a preview of something that's coming up. It seems correct. And if it is, it's very exciting. Here, Nosh is my current PhD student here in the forum. So let's start with just the definition. Some of you already helped me with this, but an orthogonal array is just a combinatorial definition. It's an n by k array. It has a strength. In this case, the strength is 2. Whatever is the strength, we're going to take a set of columns of that strength, in this case 2, pick any 2 columns, and you're going to find every pair of tuples of the alphabet appearing the same number of times. In this example here, the number of times it appears is 1. So here it means every ordered pairs of elements in the alphabet will appear if you take any 2 columns. So here is the formal definition. By the size of the array, of course, the lambda or the index is easily found. It's n divided by p to the t tuple. So if I have p to the t tuples, the index is 1 and each tuple appears once, but it could be a multiple of it. Okay, so there is connections at finite fields. I have to talk about finite fields. We'll love it. So, many important constructions, best constructions for orthogonal arrays that give the highest number of rows for an orthogonal array, finite fields, Bush construction, that exists one for every prime power of strength T, index 1 with Q plus 1 columns. For even, you can push to plus 2. And the other important one is the last one, which is an OA with higher index, but has this number of columns that we recognize from some things that we're seeing before. But Q to the n minus 1. We'll talk more about this. So this was already known from Hamming, that this is an orthogonal array of strength 2. So now let's move into LFSR. So you let a field be a finite field with Q elements, then you pick M initial values on the base field, and you have a characteristic polynomial of a sequence. The sequence is defined in the first n positions based on the initial values, and after that you start rolling the recurrence relation that comes from the polynomial. So you see AI, the coefficient of 1 is minus 1, and so on, right? The coefficients are here, minus, right? Because this is general for any field. If it's binary, it's minus and plus is the same. Okay, so this sequence is periodic, as Kirsten had mentioned, and the list period divides Q to the n minus 1, always. And then we move to M sequences, which are, the M has nothing to do with my M, which is the degree of the polynomial, but it just means maximal systems, sequences that have a maximum period. So we are interested in the sequence of maximal periods. So, well, you all know what a primitive element is. It's an element that generates the multiplicative group of the field. But also, if I have an irreducible polynomial whose root is a primitive element, the polynomial is primitive. So if the polynomial that generates the sequence is primitive, then the sequence has maximum period due to the n minus 1. And it's called an M sequence. So all the LFSR that we'll be using is M sequence, but sometimes let's say LFSR. So here is a primitive polynomial. Choose any values 0 and 2. Start building the sequence based on the recurrence relation, and you get sequence. And because this was primitive, I know the period is going to be q to the cube, right? Minus 1, q is 3, so it's 26. Okay, so this is the period is much, and then I repeat it again. So there is a lot of interesting properties. Kirsten already alluded to some. They can those that I will mention and many more can be found in this book. That's the Bible of sequences that contains chapters about sequence. Now I'll talk about the properties that I need and I would like to explore to build this arrays. First, each non-zero m tuple of FQ appears once per period as a window of size m. So this means if you pick any m, let's say the polynomial degree is 3, right? So I pick every window of size 3, I will see a tuple, a different tuple. When the tuple repeats, is because I'm restarting the sequence again. So if I told you the period is q to the m minus 1, of course the 0 tuple does not appear because I never have the 0 tuple in this. So in this case, it means I visited every single tuple exactly once. So you go here and it's a way to generate all this, the 3 tuples of FQ or m tuples of FQ. So we have that important for us. There is other cool things, for example. So this has, the period has length q to the m minus 1. Now, divide into q minus 1 pieces. Okay, so in this case, q is 3, I will divide into 2 pieces. So I have these chunks. So, and I'm copying the chunks here, right? So it is now, you see in that book, that this is a multiple of this. So this is 1 times this subsequence. Multiply each element by 2, and you'll get the other slice. So if you have q minus 1, all these chunks behave in a similar way. In particular, the pattern of zeros is identical. They line up because when I multiply a 0 by 2 or whatever, it's going to be a 0. Important property too, the part, right, that is used in some of the results. And the other thing is the 2-tuple balance property. You choose a distance, okay, but I will simplify. Let's say pick distance 1. So the number of times a certain pair appear at distance 1, 10 minutes. Oh my, okay, I better accelerate. Okay, so the number of times a pair appears at a certain distance is constant. Not so constant because there are less zeros. So it's different for the tuple 0, 0, but all the other tuples appear the same number of times at any distance you pick. So Munemasa did this. Consider an array in which, for a specific k columns here, you pick a certain k. For Munemasa was less than 2m. For us, it's going to be something up to q to the m minus 1 divided by q minus 1. But it could be something else. Just place the element in sequence here, a0 to ak. Then start from a1, and so on. Okay, so it is kind of a shift, but it's not cyclic, okay? Because it's not circulant, because the guy that entered here is the next, whoever it is, right? So this is a orthogonal array of strength 2. This is because of the 2-tuple balance property. Okay, so if I pick any 2 columns, they are at a certain distance, and every tuple appears the same number of times. So it is an orthogonal array of strength 2 with a high lambda with q to the m minus 1. And I'm doing this because I want to get to some constructions of covering arrays that use it. So here is, I'm going to look at some of the properties that will be useful for us. So here you have the sequence, shift by 1, the sequence again, okay? So I'm showing the period of the sequence here. Okay, so the rest is just repeats. But even in the period here, I want to get a chunk of a slice, right? I divide by k minus 1 and just get one of those slices. Because q is equal to 2, I will get 2 slices and I stay with the first. So that is q to the minus 1, q minus 1. Okay, so this is actually equivalent to the construction of Hamming. It is an orthogonal array of strength 2. But it also, we know more, it has almost a strength 3 because of some ideas that came from Munemasa. Munemasa was working in F2, but anyway, it's almost a strength 3 because, so some things we know here, this is an orthogonal array, right? Here I do all the 27, I have to add the row of zeros that, because the 00000 never appeared, it's added there. Also, very interesting thing because of this linear, this LFSR, the position of zeros here. If I look at the position of zeros and I look at the columns as points and points. Okay, so these are lines. These correspond to lines in the projective plane. The positions of zeros. So, for example, 0, 6, AB. But because of the cyclic structure, is actually one that is generated cyclically via a different set. So 0, 6, AB plus I are all these positions. Because of the slicing, the slices being identical, right? These are the bad points. The zeros is when we don't have the coverage we want. But the second half will repeat the same zeros, so it doesn't increase the badness of the situation. And there is, if you count, there is many more tuples that are covered than not. Because we are only not covered when you have 3 columns for which you find 3 zeros on the same row. And you count that is much less than the number of tuples that are actually covered. Or in other words, I'm looking at sets of 3 columns and seeing if they are linearly dependent or not. I can also look at something shorter here, right? This, I think, we actually prove explicitly, because we need it in our paper, Andrea, that actually you can just take the first 3 rows generates everybody, right? All the other rows are linear combination of those. And then in the paper that Brett has with Weber, etc., I could then choose other rows to generate. And what I chose is to get the primitive, powers of the primitive, each one correspond. We knew from the sequence, because the sequence is the trace of each of these elements. But if you pick the representation of that primitive that's sitting on the upper field to the 3 right here, and pick them as a basis, this is a basis. So you use the basis 0, 1, 0, 0, 0, 1, etc. Generate the sequence. This is what some rows here, and this generate the same array. Same array modulo row permutations. So we know more compactly how to represent this as that, right? Munemasa, I won't talk too much about it. This was when we started working on this, but I think for sake of time, I will not talk too much about Munemasa, but you know, it was characteristic 2. He was looking at trinomials and looking at when trinomials do not divide trinomials to count how many of the things get covered or not. Specifically given, here is an example for m equals to 3. So 2m plus 1 rows, etc. This relates to what we were seeing before. This is the smallest example of Munemasa that matches with the smallest example of us. After this, we diverge because we're looking at different sizes for K and different fields in our case, right? But here, the only places, for example, so this is one of the arrays for us for Q equals to Q. So the only place where coverage of triples, where you don't see the straight street, you don't see all the tuples appearing, are in these locations or the positions of 0. So 28 tuples, triples, have the coverage out of 35. Only 7 don't, which are given precisely by the rows of the projection plane. Okay, so Daniel did more stuff on this. Now, this is our original paper, right? And this is all the. Now, let's go to corollaries. So now we're going to restrict ourselves to index 1, even though there is corollaries with higher index and one that could be higher. But we want every tuple to appear on a column of the given strength for any strength 3, I need every tuple to appear at least once. So I relax the exact property of the orthogonal array, and I'm needing coverage, right? It's a covering problem. PK, 3 rows, and you look there, you'll find all the tuples of the alphabet appearing at least once. We are interested in looking at those. I think I will skip the definition, but maybe just the letters here. Strength T is this parameter. The first is the number of rows that we want to minimize because it's a covering. I don't know anymore what's the size, but we want to minimize N. Number of columns is K, and alphabet V. So we want the minimum for given parameters, strength, number of columns, and alphabet. I want the minimum number of rows that already exist. This is called the covering array number. To find constructions of covering arrays, we get upper bounds for this. So that's what we're doing here. We're going to do some upper bounds. Of those lower bound is VT, but it only matches the lower bound, and there is an orthogonal array of index 1, which is restrictive. I said this, but I think V plus 1 is a bound only for some T's. In some cases, it could be V plus 2, but very little. If I have more columns than V plus 2, I will never have an orthogonal array, and I will need more columns. These are used in software testing, as illustrated by Kirsten. So now we're going to use those same arrays to build subinterval arrays, a subinterval array with that number of columns. Remember, it was Q cubed minus 1 divided by Q minus 1. That's the Q squared plus Q plus 1 here. Same properties. Now, we are trying to find 2 polynomials. Sebastian Raffers, he was experimenting with different polynomials, and then we saw that there were some that worked. We stacked 2 of them, use one polynomial and another, and bam, we get a covering array. And then we noticed that the polynomials were reversals, among others, but the reversals always used, and then we proved. So we actually use this, and I do the same sequence for the reversal polynomial. Remove this because this doesn't have any coverage, and this is an orthogonal, it's a covering array. So what you prove that if something is not covered here, it is covered in the reversal. It's by the property of the tuples that have to do with this different set that appears here. And after you see the proof, it's not difficult. but yes, it works in general. So basically, I can build it in a compact way. I can actually the reversal polynomial, which is this polynomial, right? When I invert, basically flip the coefficients around, it's the same as flipping the sequence to the other side. So it's very simple. I have this, I have the opposite, the covering array. So this was very excited then. We looked at covering array table by cover. We beat the record, so our name goes there, right? and that's this bound, right? And it's not bad because, you know, for Q plus 2, I could use Q squared. But now I'm using only 2Q squared, but I can square the number of columns. So that's very nice. So I will be calling this RK in honor of Sebastian Raffers because it is this construction that gives this bound. 10 years later, is it still for this particular parameters, right? 1 for each Q out of the prime powers smaller than 23 still holds the record in covering array table. So you find Raffers, Stevens and MOURA is the same one. It's a very strong array, and I don't know if it's optimal, but it is very good, right? It's very short for the coverage that it has. These guys here then notice that actually what we have in this construction is 2 projective planes on the same points, so that they two together form a covering array, right? So what is the property? One line in one intersects a line in the other in at most 2 points, meaning that in that matrix, I will not find 3 columns in which one projective plane wrecks my coverage and the other as well. No, because if this has a 3, the other has a 2. So they don't have more than 3 columns. So they actually generalize this. You say, what about affine planes? So they prove things about, and they call this orthogonal. Okay. Mutually orthogonal is not a type of projective planes, but also affine planes. They are this definition I said. So really, Radhar's construction is two orthogonal projective planes, corresponds to it. Now, how much time? 10?
Zero.
I can go on because I'm the last, but okay, I'll be quick. This was, I had this idea that because this is so strong, maybe I could paste several copies of it and obtain a bigger one. Of course, I have to fix coverage by pasting 2 copies of this strength 3 and find something.